wherever you're joining us. Thank you for attending. We'd like to remind our participants that this is the first part of a two-part session, and each session required separate registration. So if you have not registered for next week's session on May 27th, please go back to your original invitation and register for the second session. After the end of the seminar, if we don't get to your questions and you would like to submit them directly, you can also go to our website and use the tool available for submitting technical questions, which will be directed to the correct person to answer. Now I'd like to turn things over to our presenters, Dr. Prebisch and Mr. Lucas Stromer. Thank you.
Thank you very much for the warm welcome. Again, thank you for the great opportunity to heading this ESD seminar session. And today we will focus on the basics of ESD protection. And in the next session, we will focus more on the automotive applications. In today's training session, we will start with the fundamentals of ESD protection. We will take a glimpse on the why of ESD protection, and then my colleague Jan Prebisch will take over about the measurements and characterizations we have for ESD protection. We'll talk a little bit about our Nexperia lab, and then in the end, we have some time for the Q&A session. Let's start with the fundamentals of ESD protection. So ESD is the abbreviation for electrostatic discharge, and in general, it describes a sudden discharge between persons, devices, and components. So it's a triboelectric effect that occurs. And yeah, so how does it occur? It can be that different components get together. It can be a person that walks over a carpet or something else. But the key problem is of this discharge is that it causes malfunction. So it can really harm a component and can really damage the gate oxide that we see on the pictures on the right-hand side. And the problem is those damages are not detectable. So if this ESD event happens on a system, it is damaged, we cannot easily detect it, and that's why we have to prevent those ESD strikes. Some more background about the environmental influences. So you see here a graph where the y-axis represents the voltage in kilovolts and the x-axis represents the relative humidity. And what we see is that different materials, different influences has different potential for ESD. But what is very interesting is that the more dry the air is, the more electric charge can accumulate. And this actually is very inconvenient because, for instance, in production, you want to have humidity as low as possible in order to avoid corrosion. But in effect, the potential of the ESD is very high. So the threat of ESD, of this malfunction and damages, exists everywhere. But if we talk today about ESD protection, we are focusing on the component and application level. And Jan Prebisch will now take over where we focus here and how we have to distinguish.
Yes, so as Lucas said, ESD is an event that happens everywhere in production or in daily life when the end product is used. But in order to understand if ESD will be a problem or not, it's necessary to simulate this event. Usually this is done in part of electromagnetic compliance tests in general. And for ESD, we divide between device level tests and system level tests. The idea behind this test is completely different. So device level tests are compliance tests that are in place for ICs usually, or any kind of electronic component. And you do this test in order to assess if the device will survive handling, manufacturing, and maintenance of the electronic component. A system level test, on the other hand, focuses on the overall completed system, so automotive module, completed cell phone, PC, or whatever kind of device you are designing, and wants to check if ESD that happens in ordinary usage of the device will actually damage it or not. Here, as Nexperia is a producer of ESD protection devices, we will of course look at both of these tests from the perspective of the ESD protection device and the system level view. So the very common device level test is a human body model test. This is a test which has a rather low amplitude and a long duration, and models that a human person is touching the pin of an IC and discharge. So the human skin has a rather low conductivity. This is why this amplitude is not very high, but the duration is long because it takes time that the charges actually flow into the device. The next test that is very common is the charged device model test. And this is a really sharp peak, which is very short in duration. And this models actually a discharge into a metal plate. So for example, if you have an IC which is in a plastic tube and you pour it to your table, it can charge while sliding down the tube and then rapidly discharges into the metal table. And this is actually what this test is simulating. You cannot really compare the results because failure mechanisms might be different. Yeah. The next test which you encounter from time to time is the machine model. I don't want to go into detail, but just to let you know, this is completely outdated. So it was found that it's not really representing a realistic case, and it really makes more sense to look at human body model and charged device model to assess if your device is good enough for production or not. So this to the device level test. From the perspective of the system, we are looking at the IEC 61000-4-2. Here we have a slightly different pulse, as you see, which is like a superposition of the human body model and the charged device model. So we have one rapid sharp peak at the beginning and a rather long, not that high peak, which comes second. It's not exactly a superposition, but you can imagine it like this. So this is the pulse that the system in total is expected to see in reality. From an automotive perspective, you might also consider the ISO 10605, which is looking very similar and has just a slightly different discharge network. As I said, it's part of ESD. So in testing a complete module, you have capacitive or near-field coupling effects which come into account and stuff like this. But here, from the perspective of an ESD protection device, which you test, it's a superposition of the charged device model and human body model test. One difference which is also important is when you test a device model, you usually start with one value and then incrementally increase until the device fails. And then you have a safety margin, and then you can rate your IC to 2 kV human body model or whatever is the result of your test. With system level testing, it's usually the other way around. So depending on where you want to use your system, you have a requirement to fulfill a certain level. So you are testing, let's say level 4, and then you have a certain value for contact discharge and air discharge and a certain procedure to do your test. And if your system is still working at the end, you are pass. So it's a different idea. However, when you look at ESD protection devices, this IEC test pulse is very often used as a device characterization test pulse. So it's also incrementally increased till destruction. And the reason is that ESD protection devices are robust enough to be handled in production. So you really don't have to care about human body and charged device model for those. But you want to understand how it behaves in a real-life application. Okay, these two different pulses or parts of the pulse can cause different failure mechanisms. The first one, the high peak at the beginning here, which is similar to the charged device model, and this is usually causing problems with oxides of MOSFET inputs. So if you think of a high-speed data interface, which has a complementary CMOS interface, the gate oxides are the thing that gets destroyed first by the high voltage peak. The second here, which is very often called the shoulder of the pulse, is containing the vast majority of the energy, and this is causing thermal destruction, which is then usually referred to as electrical overstress, or EOS. So if someone says it's an EOS failure, it can be ESD, then it comes from the shoulder here, or it can be a high energetic surge pulse that comes from lightning strikes or any other kind of coupled energy source. Okay, if you open up an IC and want to understand how it is destroyed, it's very often not possible, and sometimes you find some hints, like here, for example, this burn mark near the source, which indicates that the gate probably had a problem there. And this is something which is really obvious, EOS. So this trace inside the transistor just melted because of a too high current density. To prevent this and to be used in practice or in manufacturing, ICs usually have an internal ESD protection. And if an IC vendor comes to you and says, well, we have a very robust IC because it has an internal ESD protection, well, every IC has an internal ESD protection. It's not something fancy, or so it's standard, because otherwise you would never reach the levels you require for handling. Yeah, and this here on the right side is an example circuit. It's rather complicated. I don't want to go into details for this, but just to let you know that there are usually several stages of ESD protection devices for several inputs. And yeah, the ESD pulse is entering here at the I/O pin and can be clamped to ground via this clamp. Is a bit reduced by the resistance here, which might be on purpose or not. And then here are additional protection devices inside to prevent the voltage level at the gates becoming too high. Yeah, but the goal, because of cost reason and because of system design, is just to survive the handling. Yeah, system level perspective looks a bit different, which is Lucas now going to introduce.
Yeah, thanks, Jan. So an example here is a P-channel trans MOSFET from an Xperia portfolio. And then, as Jan described, so we really have to distinguish between the device level robustness and the system level robustness. And what you can see here in the schematics is that we have the internal ESD protection within this MOSFET. And from a device level robustness, it survives up to 2 kilovolts. And again, those 2 kilovolts robustness is definitely enough to survive the assembly process on the PCB or the body model robustness, but it is not sufficient for the system level protection for the whole application. In general, as we know in the semiconductor world, the trend of the Moore's law, we have the trend that the feature size of these ICs is shrinking more and more. What you see here on the gray area is the feature size, and then we have the red area within this IC model, which is the dedicated internal design space for the ESD protection in order to achieve, in this example, 2 kilovolts of human body model robustness. And if we now shrink the gate oxide, make it thinner, and shrink the whole feature size of the IC, we turn to happen that the design area we need for the internal ESD protection actually exceeds the feature size of the IC. So we are now coming at a gate oxide thickness of about 1.5 nanometers. And here we clearly see the trend. In order to still achieve 2 kilovolts, we must spend so much IC area to achieve this. And there's definitely a breaking point. What you see also here is just a trend of the human body model targets for high-speed interfaces. They were lowered within the last couple of years. So the general trend is that we face ICs become more and more sensitive. And as such, device level robustness, yes, they might be sufficient enough for the assembly process, But in order to have a good system level robustness, we need more dedicated discrete ESD solutions and have an external protection concept. To explain it a little bit more, why we need external ESD protection. You see here a model, and in this model we have here the IC, and if we wouldn't have any external ESD protection, the only way for the ESD current would be via the internal ESD protection down to ground. If we add some resistance and inductance which comes from the traces and position an external ESD protection here right behind the connector, then the whole setup works as a current divider. And then in the case of an ESD event, the current will move through this ESD protection. Yeah, so we can actually use those parasitics we have here for our benefit, and in effect increase the system level robustness. On the table on the left hand side, you can see different ICs and transceivers for the very common CAN bus. And in the middle column, you can see the ESD device level robustness of the ICs itself. And what you can see, if you add external ESD protection, in that case, our IVN product, we extended the system level robustness to a level of 30 kV, which is really robust and gives us the good protection behavior in order to secure the application. So this was basically the first step of our ESD Seminar Session 1. So we talked about the fundamentals, and now we will move on talking more about what are the selection criteria of ESD devices. So where do we have to focus if we select a protection device? And then Jan will talk a little bit more about the different measurement and characterization tests for ESD protection devices. So if we as engineers want to select an ESD protection, one of the first things we think about is what is the PCB space we can spend for the external ESD protection. And there we ask ourselves, what is the package? So what is the size? What is the footprint we have available? What is the application? And by that we can decide on maybe leaded packages or smaller leadless packages. When it comes to leadless packages, we also have the option of side with lengths, which is a feature on the side of a package, which allows optical inspection and makes manufacturing process more reliable. Then we also have questions of the number of signal lines, also dependent on the application. And then we have plenty of electrical parameters, like the reverse standoff voltage, the device level robustness itself, clamping voltage, dynamic resistance, the typology should be unidirectional, bidirectional, capacitance we add as parasitic to the signal line, and others more. So there are a lot of selection criteria, and in the following we selected the most important ones. And now I will hand over to Jan.
Yes, so here we are going to cover actually the first 4 points. And in the next week's session, we will also dig a bit deeper into different topologies and the role of the device capacitance. Today, the focus is on the characterization of the device itself. Usually requirements on those come from the application and are not critical to characterize a device. So first one, the number of lines to protect. This seems to be very trivial, but it can be a source of more freedom in day-to-day design, to put it maybe like this. Here as an example is a USB 3 connector. You see the high-speed data lines routed here through this array of pins. And on the other side, you see the ESD protection devices here, which are protecting multiple lines at once. This has some benefits. One is that you can actually match the parasitic capacitances, for example, but also the inductances and other parasitics and the electrical behavior of the devices internally. So you can guarantee that there is no big deviation from one pin to another. However, in practice, and especially when it comes to high data rates, like in USB 3, this is actually not needed because the parasitic capacitance of the devices is so low that the relative deviation can be rather high. So you can also select single devices to protect every data line. This has some benefits, like shown here. This is a USB connector of a cell phone. And you see here this tiny devices. These are all ESD protection devices, and you can see that you can place them closer to the connector, which gives you a higher robustness, as Lucas already explained, and it gives you a bit more freedom when it comes to routing, because otherwise you always have to route your traces to the ESD protection device. If you have a single device, you can put it where you want. Yeah, so it depends a bit on what you're looking at. For example, for standard automotive interfaces like CAN, probably a single device really makes sense because the matching is important, because the capacitance is rather high, because it's not that of a high-speed data link. But if you think of gigabit Ethernet, for example, this might also be an option. Okay, next parameter is the reverse standoff voltage. This is a standard parameter you find in every data sheet, and is usually known what is needed, but it causes a lot of misunderstandings very often. So the reverse standoff voltage gives you a voltage which guarantees you that the ESD protection is not activated. Yeah, so here in this case, for example, you can apply a 24-volt DC, and the ESD protection will act as a very high ohmic and low capacitance device, and not acting as an ESD protection device. The breakdown voltage is actually the transition from the device being a turned off parasitic effect to an active ESD protection. This is listed here. So in this case, typical 30 volt. So what is guaranteed is that the breakdown voltage is always above the reverse working voltage. Another reason why this is stated in the data sheets is that at this voltage, every test is done. So you could also use this for, don't know, 12 volt or 5 volt or whatever you encounter as DC on your line. But all the tests are conducted for this 24 volts. So in this case, the leakage current is also evaluated at this voltage. Yeah? So it's just a reference, but it does not guarantee you anything. So for example, if you want to protect a CAN bus and you are having a certain requirement for DC robustness, then you should not only look at the reverse working voltage, but also the trigger voltage or the breakdown voltage. The leakage current here, always a typical value is defined. One thing to mention here is that because of physics, basically for any technology, leakage currents are increasing with temperature. This is usually also shown, it's common to rate the device at room temperature and to provide such information if required. But usually leakage currents are no issue for modern ESD protection devices. Next is the ESD Tolerance Test, or the ESD Robustness of the ESD protection device itself. As I already said in the beginning, there are different tests for device level and system level. And here we actually conduct a device level test, but because we want to understand the robustness against system level conditions, a system level pulse is applied. So this is according to the IEC 61000-4-2. Here you see the drawing out of the norm. So actually there are a lot of tests that you have to conduct when you want to comply with the norm, like shooting into this vertical coupling planes and having air discharge and stuff like this. But for a single device, this does not tell you anything. The only reliable and repeatable thing you can do is to directly shoot on the device itself and to consider it as a system. Air discharge also does not really make sense, and the repeatability is not very good, especially because the single devices are so tiny. So usually in basically any case, you can say that the robustness for air discharge is at least the same as for contact discharge. So if you have a device that survives 20 kV contact discharge and you are questioning if it will survive 80 kV air discharge, it will. Okay, how to test if the device is still alive or not, if you have a failure. To do this, we measure the IV curve of the device, and therefore we are checking if it still behaves as an ESD protection device afterwards. So it's very high ohmic low capacitance. When not used as an ESD protection, in case of an ESD event, it's becoming very low ohmic. And then we increase the applied ESD voltage until destruction, and therefore define the robustness of the device. Here's an example from a data sheet where you have contact discharge to compliant with the IEC pulse. And here also, because it's an automotive product, against the ISO pulses with different discharge networks. But the procedure is the same. One thing that is very important to understand is that the device robustness itself does not correlate with the system level robustness. Yeah, so the device itself has to be as robust as your requirements are, that's for sure. But you don't have to have an extremely robust device. So this is an extremely robust device with 30 kV, so you don't have to worry about this. But especially when you look at high-speed interfaces, you have to, there are some trade-offs. Especially if you want to have an extremely low parasitic capacitance of, let's say, below 1 picofarad, it's very hard or even impossible to achieve 30 kV. But it's also not really needed, because the first thing that dies in your system is usually not the ESD protection device, but the IC you want to protect. So it's more important to understand how they interplay. And one parameter for giving you an understanding here is the so-called clamping voltage. The clamping voltage looks in a data sheet like this. It's also based on this IEC 61000-4-2 pulse, here 8 kV. And then there's a graph shown, and at a certain point in time, here 30 nanoseconds, it is evaluated and it says 24 volts. So what it tells you is that if you have your interface and you are shooting on the connector, the voltage peak of 8 kV is clamped down to this curve. So you can understand it that more or less this is what the IC sees during an ESD event. And because most interfaces, especially in automotive and let's say not that high speed interfaces like let's say CAN bus and also USB 2 or something like this, are usually not that fragile when it comes to this very sharp peaks. So this is why it's evaluated here after 30 nanoseconds. And the procedure to derive this this value or this graph is the following. You have your ESD generator, which is the ESD gun, the device under test, and an attenuation network because you don't want to destroy your scope, and a scope to measure the voltage at the device under test. This looks very simple, but in practice it's actually a bit tricky. So first problem is that a scope is usually not shielded very well, and also a bit sensitive when it comes to secondary effects of ESD, namely the coupled energy from the ESD gun, which is also usually not shielded very well. So to have good results, you have to shield your ESD gun. Here, an example is this is a shielding chamber. We cut a hole in the side, and here is a small target where the ESD gun is shooting at. Here, this short cable is the ground connection. And on the other side, you have an outlet with an SMA connector. And here we have a test PCB with a 50 ohm transmission line. In the middle, there's the device under test, and then we connect our scope. Now, if you do not shield the gun from the scope or from the PCB, you will not get repeatable results, and you will definitely spoil your measurement results significantly. Another thing you should look at is the bandwidth of your scope. This is an example from a data sheet. This is a clamping curve, and this is what comes out in the measurement if you use a proper scope. The reason why you need this is that, especially at the beginning, the sharp peaks, if you undersample, you will just miss them. And this is why you here have around 70 volts peak, and the 30 nanoseconds value is comparable to this one. So this is okay, but especially the first peak is not presented very well. Another practical thing to look at is the cables. So here, this should be a rather short cable to the scope. Otherwise, you will definitely get reflections. Because ESD is an RF event, you have also to treat it like this. Here is a comparative study we did once. This is not the cable you just saw, it's the cable, the ground cable that connects the gun to the shielding chamber. This is here a very short one, just 12 centimeters. And on the left and right, it's always the same device under test with a short cable and a long cable of 2 meters. And you see here that you have a very clear and distinct waveform. On the other hand, if you have the long cable, the beginning looks somehow the same, and then you have something that is not representing what you would expect. The same for the other examples also. The reason is it's an RF event, and the 2 meter long ground cable is long enough to actually cause reflections between the reference of the PCB, where the device under test is, and the gun. So actually waves are traveling back and forth, and you have constructive and destructive superposition of those waves, and your results are not clear anymore. So this is the clamping voltage, but when you look at a data sheet, you have to be a bit careful, because there are usually several clamping voltages stated. And unfortunately, always the same name is used. So one clamping voltage is you shoot at the device under test, and you record the waveform to get an understanding what the IC would see during an ESD event. And if you compare different protection devices, you should always look for the lower clamping voltage, of course, because it protects your IC better. The second clamping voltage you encounter, this one here, is not for the IEC pulse, but for a surge pulse with 8 microseconds rise time and 20 fall time. It's also from an IEC standard, the 61000-4-5, which is defining the surge pulse. And it's defined as the voltage amplitude, the maximum you see when you apply this pulse of here the given amplitude of 3.5 amps. The 3.5 amps are coming from the maximum current the device can survive. So very often you are looking at the maximum current the device can survive with respect to this pulse because it gives you an understanding how much energy the ESD protection device can bring to ground without being destroyed itself. So the higher the maximum current, the more robust the device is also against rather slow and high energetic pulses. And from this, you can actually conclude how robust the device is, but you cannot conclude how good the IC is protected. And to understand this, at the maximum current that can be applied, the voltage maximum is evaluated. And this is then referred to as the clamping voltage. Yeah, okay, so data sheet, and you already got the second clamping voltage. But again, the lower the clamping voltage, the better. The next clamping voltage is coming from the TLP. But before going to the TLP, one additional concept, the dynamic resistance. So Lucas showed you in the beginning this very simple model where you have an IC with an internal protection, you have some parasitics from the PCB, and you have your external protection. Here we draw a diode, and the diode, someone breaks down into reverse. But the question is, how good does it actually break down? And the answer for this is the so-called dynamic resistance. So here the idea is that any voltage I see at this node, I should be able to calculate, at least in first order approximation, by knowing the breakdown voltage of the device and the current that is flowing through it. And then I have a certain resistance that links the current through the device with the, at the end, clamping voltage. Yeah, so clamping voltage was always referring to a certain current or a certain amplitude of the pulse. Here we can actually exclude this value by just looking at the resistance. Yeah, so the lower the resistance, the lower the clamping voltage will be. Yeah, so it gives you a more generic value. So the dynamic resistance should be as low as possible, because the current divider that is formed with the external ESD protection is becoming better if the dynamic resistance is lower. There are two approaches to define the dynamic resistance. One is based on the surge pulse, the H820 pulse you just saw, and the other one is based on the TLP. To understand how this also works with the surge pulse, we will go into the TLP measurement, and at the end you will see the result, and you can then understand that you can do the same for the surge pulse. Okay, TLP, transmission line pulse. The idea why to use an additional testing method, this TLP method, came from the observation that the repeatability of ESD tests is very poor. And also, if you have a very good setup, you have problems when you, for example, use ESD guns of different vendors, because the IC specs are very wide. The window is very, very large, and you cannot really understand what is physically happening if you have this complex pulses that are exposed to your system. So the idea was to have a very, very defined environment of a 50 ohm transmission line, and to have a high energy pulse which is traveling down this 50 ohm line. So here on the left side you see the generator. Then you are charging up this transmission line, you're closing the pulse, the switch, and what results is a nearly rectangular pulse which is traveling down this transmission line and then hitting the protection device you want to characterize. And what you measure is the voltage across the protection device and the current that is flowing into the protection device. Because it's a 50 ohm line, what will also happen is that parts of the pulse are going to be reflected and they are absorbed in the generator. So you don't have this back and forth bouncing effect you have when you use an ESD gun with a long cable. Okay, so this is the theory. In practice, the device looks like this. So here, this is the generator for the pulse. Here, this is our setup to actually connect on a wafer to test ESD protection devices for high-speed links, which are basically bare die. But of course, it also works for leaded devices, and we actually very often use it to characterize also internal ESD protections to understand if it works well together with the external one. So this is the result for an example device. So the current that is flowing into the protection device, so nearly rectangular. You see that here at the beginning there's some activation process going on, and then you see the rest of the rectangular pulse. It's not ideally rectangular. You have a length of 100 nanoseconds and a rise time of 1 nanosecond. And there's also an option called very fast TLP, which is a shorter one, to actually have a closer look on the turn-on behavior. But this is for 95% of the interfaces not relevant, but this is becoming interesting if you look at really advanced and high-speed cutting-edge technology. But especially if you look at automotive, for example, usually it's not of importance because everything is rather robust. In the voltage, you see something similar. So this is the voltage across the ESD protection device, and you see that here is an overshoot, like with the clamping measurement. Then the device is activating and coming to steady state voltage here. And what is done is that you shoot or you excite the ESD protection device with increasing amplitudes of the rectangular pulse. You record voltage and current. Then you average in a window between 70 and 90 nanoseconds, and then you get a point on an IV chart. So the result is a so-called TLP curve, which you can understand as an IV chart for the pulsed condition. So actually how the device behaves under ESD. And the length of the pulse is comparable to an ESD event. And if you want to look at the first peak, you can use the very fast TLP to characterize it the same way. You will also get a plot like this. This is the result for a realistic device. The one you saw before. Here, the device is very high ohmic and low capacitance. Nothing is happening. If you exceed the certain trigger voltage, the device is activated. It's actually snapping down a bit, and then the curve becomes rather linear. And this slope, this linear slope, is the dynamic resistance. So the more steep the curve is, the better the device is. This is the general rule. If you compare different devices, you should always consider to be as left as possible, because the more left you are, the lower is the clamping voltage. Here, for a given current, let's assume 40 amps, you arrive at 40 volts. And if you compare different devices, the more left you are, the better you are. If you want to understand if a device is working well together with an internal protection, you should also consider that the internal protection should somehow behave or have a curve or a measurement curve on the right side, so that in the case of an ESD event, the external protection is actually activated before the internal does. Otherwise, it's not helping. So this is the general idea. Of course, you have some boundaries, like for example here, this diode is for CAN and LIN bus, and you have to be short to battery robust, so you cannot go as left as you want, but you should be as left as possible to have a good protection scheme. More details on this we will discuss next week with respect to the different interfaces we see in a car.
Thank you, Jan. So again, to summarize, we discussed about the fundamentals of ESD protection. What is ESD event? What are the key points we have to focus on? We discussed about the selection criterion, and then the most important measurements and characterizations. And as Jan said, so this was now the theory, and in the next session we will then see in practice for the different applications, different protocols, what are the key points where we will have really application examples we will discuss with you, and also have comparisons, for example, with the dynamic resistance to see what are the different protecting behaviors of different ESD solutions. To sum up the first session, I just want to give a little glimpse of our Nexperia lab, what we do, and then we will open up the Q&A session afterwards. So at Nexperia, we have really a dedicated team which is focusing on ESD solutions which are needed for the applications. And within this laboratory, we have all the measurements, or we can do all the measurements Jan presented before. So we have plenty of analysis tools. We have TLP generators, we have ESD guns, we have different characterization models, but we can also do a lot of simulation work. So the so-called seed simulation, system efficient ESD design, S parameters, SPICE models, and many others. This is where we can help to make design review or do error tracking applications, or simply characterize devices. Something I want to pin out here is the so-called EMI scanner. EMI stands for electromagnetic interference, and this EMI scanner allows us to measure the magnetic field on the PCB and actually show the current flow. So we have here the setup of such device, and what we get from this EMI scanner is a video. So if we do the ESD parts, this EMI scanner really films the current flow on the PCB. And what you see here on the left-hand side is the PCB without external ESD protection. So you remember the schematics we showed before. So there's no external ESD protection. It's just the network, some resistors, inductances, and then we have here the IC. And in the event of an ESD, with the help of the EMI scanner, we can see that the ESD current really flows through the traces into the IC, and here it can cause this malfunction and those gate excite damage. If we place external ESD protection right at the connector, in case here it's a CAN transceiver, same PCB, same setup, but now with the external ESD protection, we have the ESD parts, and we can see that the external protection is triggering and it's clamping down the ESD current. And here in this color coding, you see that the majority of the ESD current is in front of the PCB at the connector. It does not go through all the traces, and the IC is safe. And this is something we can do within our laboratory. To sum up, we not only have, of course, the lab. You can find a lot more details, especially if we take a look on the product portfolio on our Nexperia webpage. So there we have a cross-reference and parametric search function, and on also a very good product overview of what we offer. You have data sheets, different application examples. If you like book overview, we also have our selection guide as PDF available. And the fundamentals we discussed today, and even more details and more information, is written down in our ESD application handbook. So there we have all this information written down. It's available in hard copy in English and Chinese version. And yeah, a highlight for this year is that we are now working on a dedicated automotive version, which is coming this summer. And as I said, so we can offer lab support if you have questions. So this is it. This was the very first session of the ESD seminar. Thank you very much for your attention, and would now like to open the Q&A session for you.
Yes, so there was the ability to type questions in the question pane, as it was mentioned at the beginning. There are plenty of questions, so I'm not sure if we can go through all of them, but we will give it a try. So first of all, the presentation you can download at the sidebar under the tab Handout, and we will make it available afterwards as well. Then the question here was, do you have ESD generators spice model with air gap resistance modeling? So we are actually working very hard on the modeling aspect, and we focus on the modeling of our devices. So we have, of course, models for ESD generators, but not including any air gaps or so, because we are focusing on repeatability of results. So our effort is in cooperation with the ESD Association and Working Group 26. This model or link technique is called SEED, System Efficient ESD Design, and we are providing on request SEED models, which are very complex and including the complete turn-on behavior and everything you saw on the TLP slide in the model. But this is something you should know what you are doing if you're using a model like this. If you download the standard models from our website, they are signal integrity optimized usually. Yeah, so they are not suitable for modeling actually ESD devices, because what's happening in the device is extremely complex, but it's modeling the RF behavior of the device. So if you want to understand if it's good enough for signal integrity, those models are suitable. But if you want to model or understand what's happening exactly during the ESD event, yeah, SEED is the answer. If you go to our webpage, you also find a white paper on this SEED methodology applied to automotive Ethernet according to Open Alliance, which we published beginning of the year. Okay, then next question is, based on your photos of failure models, an ESD failure is not only pinholes but also burnt polysilicon or metals. Yes, that's true. Basically anything can be destroyed. You even see melted bond wires, not directly from ordinary ESD events, but from search events, for example. But afterwards, it's impossible to distinguish what actually happens when the IC was destroyed. You know, you have to, if you want to find out what happened, you have to reconstruct what the situation was. From opening up the IC, you usually cannot understand what kind of pulse this was. It's really hard because you have to destroy it on purpose and see if it looks the same or not, and it's yeah, not really reliable, to put it like this. And then the next question is, in slide 10, it was mentioned that the peak, so the shoulder of the ESD event, do designers have to compute the area under the ESD waveform to select the proper ESD protection device to reduce the second peak? Not really. It's a good question because it depends on the energy, but what you can do to get an understanding is to look at the IPPM, so the maximum current rating, to get an understanding how much energy the device can push to ground. And the clamping voltage is the more important parameter if you look at ESD system level robustness. Okay. Yeah, Lucas, if you want to say something, just say something. Yeah.
Yeah, we just, so we get so many questions, we just have to scroll down here.
Yeah.
Just a side comment on the search robustness, or especially ESD robustness, since we talked about also the size of external ESD protection. So in general, if you want to have a really, really robust ESD protection device, you have to certainly spend some silicon area. And if you really want to have high search robustness, for example, with the TVS portfolio we offer, then we also have to spend more silicon area. So there's some sort of a trade-off. Sometimes if you have very high frequency applications, or also you have very few space available and you need a small package, then of course also the size of the ESD protection is limited, and in effect this lowers the robustness. So this also has an influence on it.
Okay, so next question. You recommended single line devices for gigabit Ethernet. Is it also it's also very sensitive to balance? How do you recommend maintaining the capacitance matching between Ethernet lines with separate devices? Yes, I don't want to recommend to use single ones. I just want to mention that it's also possible to use single ones. And the reason for this is that the relative deviation of the capacitance of the devices is more or less the same if you have a 20 picofarad device for CAN, or a 2 picofarad or 1 picofarad device for gigabit Ethernet. So let's say you have 10%, then you have a maximum deviation of 2 picofarads for the CAN device, which might be problematic because of the asymmetry. But if you have 0.1 picofarad deviation looking at a 1 picofarad device, it's in a range that usually does not affect too much, because you also have to account for other devices and their inaccuracy, like the COM mode choke, for example. This is why when the absolute capacitance of the protection device is going down, the matching is becoming less and less important. Yeah, this is just what I wanted to highlight. Of course, you cannot, if you have two separate devices, you have to live with the deviation those have. You cannot pre-select them or something like this. Okay, then there's a question on the difference of the reverse working maximum and the breakdown voltage. The reverse working maximum voltage was the voltage where the device can be used with DC, for example, and is not acting as an ESD protection device. The breakdown voltage is a voltage that is higher than the reverse working maximum voltage and gives you actually an indication at which voltage the transition from not being an ESD protection to an ESD protection device is, or behavior is happening. Yeah. So to put it like this, very, very, very simple ESD protection devices are Zener diodes, and the reverse working maximum voltage is some voltage that is lower than the breakdown voltage, and the breakdown voltage is where the curve starts to become exponentially. Usually in data sheets, you find a statement which current is the threshold to define the breakdown voltage. It's usually 10 milliamp. And the reverse working maximum is where the device has a very, very low leakage current of a nanoamp or something like this. So this is basically the difference. And this is also the reason why there's always a gap between the reverse working voltage and the breakdown voltage. So if you think of a simple Zener diode, it's the difference between 1 nanoamp and 10 milliamps. Okay, so next questions. So there's a question, do you recommend any kind of oscilloscope probe to measure ESD impact over DUT? Yes, the best probe is no probe, because the field coupling is also coupling to the probes. So if you are able to somehow design a system which the one that was on the slide, where you have somehow defined transmission lines and connectors, is always the best. Otherwise, yeah, you have to use a probe which you can use to actually probe in the system where you want to probe. But yeah, no further recommendations according to this. Okay, So there's the question what a SEED model is. SEED model stands for System Efficient ESD Design. It's a topic we could easily talk for hours. It is a simulation method which is working with equivalent circuit models or behavioral description models, usually implemented in Verilog or VHDL. And this is actually simulating what is happening during an ESD event. You have to characterize the system extremely accurate. Usually use TLP to also characterize the nonlinear effects of the passive and stuff like this. And it allows you to understand what actually happens and where the current is flowing and how and when the ESD protection devices are triggering. And this is actually required when tuning high-speed ICs with suitable ESD protection devices. Yeah, so slide 44, 3D solver simulator. No, on slide 44, you saw EMI scanner measurements. So this is a device where we have an H field probe, which is above the PCB. Then we inject a pulse and record the H field in X and Y direction. And from the H field, you can calculate the current that is flowing on the surface of the PCB. So the result of this measurement is the current that is flowing on the PCB. So it's an actual measurement. Yeah, then Lucas, can you go back? There's a question on the left corner why it's red. So the reason, if you compare left side and right side, and you will observe that on the right side with protection, there is less current at the IC, but there is a bit more current on the top of the PCB. And this is because there is the ground connection of the PCB and the current has to flow somewhere to ground. And here, the current is flowing directly on the left side of the PCB from the ESD protection device to the upper edge where the ground is connected, while on the left side where there's no external ESD protection, the current is flowing into the IC and then on the opposite side of the PCB to the upper left edge of the PCB, where you also see that it's getting a bit greener. Yeah. Then lab support, please indicate cost.
So as we said, we offer the lab support for you in certain cases. So this is not a general service we offer. So this is only really on customer request, and if you get into contact with us. And in general, there's no direct cost affected with our lab support, and it really depends on the individual case. For instance, if we need to produce new PCB designs or take additional lab equipment into consideration, then yeah, it depends on the individual case.
Okay, so we have 10 questions left and we are already 5 minutes over time. So I guess we are going to answer the last 10 questions via email. End the session here. If you have any further questions, don't hesitate to contact us via the webpage, or if it's related to the presentation, of course, also contact us directly. Our email addresses are on the first slide of the presentation.
Thank you, everyone, for joining and taking the time out with Nexperia. Presenters, do you have any final remarks before we close the training?
Thank you very much, and see you or hear you or talk to you next week.
Thank you, everyone. Have a great day.
Thank you. Bye.